आ गया ना? Okay, start. Good afternoon, everyone. Welcome to the week 12 live session on structural dynamics course. I'm your TA from IIT Madras. Okay, so in last week 11, we studied about we continued our discussion on multi-degree of freedom systems, and we also had some derivations there, proving the symmetric nature of stiffness matrix and the flexibility matrix. Later on, we also studied the concept as orthogonality of modes and what are its practical implications. That's what practically it means by the orthogonal modes. Okay, so at that time we stopped the discussion there. But today we will be continue. We will not be continuing with the same thing, multi-degree of freedom systems. But today, in the last and the final session, we will be studying something new concept known as dynamics of the continuous systems. And in the online module, I think week 12 is going on live, wherein you guys are dealing with the modules like vibration control, introduction to vibration control, active control, passive control, design of tuned mass dampers. We will not be discussing that thing here. In fact, I will discuss the modules of the week 10 in today's live session. Dynamic response of continuous systems, where vibration of the continuous systems will be discussed, such as the vibration of the taut cable, vibration of the longitudinal bar, or transverse vibrations of a beam, or we can have the vibrations of a shaft under rotatory motion. Okay, these things we will be discussing today. We were not able to cover all the modules that are present there in the NPTEL portal, but I tried to cover most of the topics that are listed there in the site. Starting from the basic concepts, we discussed that thoroughly in week first. Then I discussed free vibration of single degree of freedom system, and in we also studied that thing thoroughly, and deriving the equations of the motion for all kinds of vibrations, such as forced free and forced vibrations, which included damping and which were not damped as well. Then continuing, we studied all the relation between different parameters such as deformation response factor. We had that the transmissibility ratio was there. There were many parameters that we studied in detail, and then we also studied this force transmission topic and the vibration measurement. I told you about the half power bandwidth and all those concepts. Then one of the important topics that we studied was the response to arbitrary motions, where I gave you the full discussion on the unit impulse. Yeah, we studied about Dirac delta function. We studied about what is that known as Domal integral. That is the important integral in deriving the response of single degree of freedom or multi-degree of freedom system subject to impulse loadings. I told you about what we meant by impulse function. Okay, then we derived the response from the first principle, as well as using Domal integral for single degree of freedom, single degree of freedom system subjected to rectangular pulse, triangular pulse, half sine pulse, and full sine pulse. Maybe I think we studied the derivation from the first principle only for step pulse, rectangular pulse, and half sine pulse. Later on, I said you it's a part of your homework. You study the response of single degree of freedom system under a full sine wave. Okay, then another 1 week I dedicated the whole week for numerical methods of the solution for deriving the response of a single degree of freedom system, because I told you that can be extended to the multi-degree of freedom system as well. But I think that was not the part of your syllabus, so I discussed only single degree of freedom system, where I discussed time stepping methods such as implicit method, explicit method, there was main method, central difference method, there was Wilson theta method, there was Newmark's method. If you go through all the presentation slides that I have uploaded on these NPTEL that have been shared with you guys, we can find all these details in that one. And same are being given in the video lectures as well. Please go through the video lectures carefully. So after that, we studied multi-degree of freedom system, one of the important topics. Therein we derived the equation of motion for multi-degree of freedom system, studied what is about meant by natural frequencies and mode shapes, that is the modal characteristics of our system, and how they are dependent on each other. Then we, in the last week, I gave you the important discussions on the modal orthogonality. Then there was one topic known as approximate methods for finding the natural frequency. Where is we have, I guess it's known as Rayleigh-Gibbs method. One is Rayleigh-Gibbs method, another is something they are known as, but we didn't discuss it. That thing you can do that thing on your own. We didn't discuss it. One of the important part of this syllabus is the earthquake response of multi-degree of freedom system, because we didn't have that much amount of time that we will discuss that thing. But today I am discussing one of the important things, that is the dynamics of the continuous systems. So far in all the topics that we have discussed in the 11 weeks, you people have seen that we were defining our degrees of freedom, or we were defining our parameters of our system, that is mass, stiffness, damping at discrete points. Okay, so for example, we were making the mathematical model for all types of single degree of freedom systems like this. Okay, I was saying that this was mass, and it is stiffness is lumped like K. It is I mean to say that it is damping is also lumped like C, and then we derived equation of motion for the same thing. So, but this is one of the idealized cases wherein we solve the equations of the motion. You people were saying that even if idealizing the single degree of freedom system to such a simpler concepts, we are getting more complex and complex equations once we were incorporating more and more factors like free vibration, forced vibration, then going into the categories damped and undamped systems as well. So complexities were increasing as we increased the parameters in our dynamic models. So, but this is not the case in the practical scenarios. For example, and one more thing, I told you in multi-degree of freedom systems, I told you we studied these frames in detail, wherein I showed you how we can derive the mode shapes and the model. In short, how we can derive the modal characteristics of the frames. I told you, na, but it's not the case in the practical scenarios. Like these were columns and these were floor systems like this. Okay, I told you. For example, these are below columns. We didn't consider their contribution to the system, but I told you, if we considered this column, and this floor system, we considered the whole mass to be lumped at a single point like this. Okay, we considered this as M1. Okay, and defined the degree of freedom at that point itself. Okay, then the mass of this column. So let me show a different one. Okay, the mass of this column, and this above floor system. I told you this whole mass is lumped at another point here, M2. Okay. M2, and define at the degree of freedom, another degree of freedom, X2 there. So this was our single degree of freedom system, how we studied the discrete single degree of freedom system, and how we studied the discrete multi-degree of freedom system. In multi-degree of freedom system, we usually concentrated or lumped our masses at the points where we are required to define our degrees of freedom. But in actual cases, this cannot be the scenario. We cannot, if these floor systems are very large and these columns are very huge, which are in practical cases, we cannot neglect their distribution. We cannot neglect their shape, their types of the shapes of which they are formed. So we have to take care of their all the other parameters, like how is the distribution of the mass along the floor system, how is the distribution of the mass along the column system, because and also how is the distribution of the stiffness along the floor system and along the column systems as well, because that things are eventually going to change the whole dynamics of our system. So at each and every point in our system, we treat these continuous systems that each and every point in our system will is having tendency to vibrate. So we call these systems as system of infinite degrees of freedom. Okay, so the approach for this type of system of infinite degree of freedom system is similar to that of single degree of freedom system or discrete degrees of freedom system, but we have to do something additional things in order to arrive at the equations of the motion. So I'm saying that we are here having this we call as, let me write for you people here, discrete discrete systems. Okay, system. So the mass was lumped. Okay, mass, stiffness, mass stiffness, and damping. Damping was lumped at certain points. Okay, so this was the case in this thing. So in mass, stiffness, and damping, all the parameters are being taken care for. So in mass, you usually have the geometric shape of the system. In stiffness, you have the material properties like Young's modulus, shear modulus, because those guys are taking care of the stiffness of the system, and geometry as well, because there is geometric contribution. Contribution to the system comes from the geometry of the system as well. Okay, and the damping, one of the important parameters in our dynamics, and same comes from the we consider damping to be concentrated at certain locations as well. But this is not the case in practical scenarios where, for example, we are having a beam. Okay, we are having beam section like this. It's tapered like this. Okay, so it's having something like this. So we are having A1 cross section here like this, A2 cross section here like this, and we are having different types, different distribution of the reinforcement inside the beam, and we are having different densities inside it. We are having rho 1 here, rho 2 here, something, it's totally random, and do we cannot do the concept of lumping the mass at a single point, and this whole system is having a tendency, for example, if I take one point here, it's having a tendency to show motion here, w along x comma t, it's having motion into w1. This point will again show has the tendency to vibrate. Okay, w2 x comma t. Okay, it occurs when it's being acted upon by some time varying force. Okay, we have force acting on it, q of x comma t. Okay, so the all the parameters are function of the position as well as time. That's why it's called as dynamic system. Okay, so we have to think about case how we can solve these types of systems using the same mechanics concepts, using the same second law of motion, using the same concept of the free body diagrams. Nothing is going to change here, but our approach in solving the problem is going to change here. All these physical concepts are going to remain constant. Okay, so in today's live session, we will be dealing with these type of continuous systems only. And this is the case in the practical scenarios, because we will be dealing with the beams of different shapes, different sizes, different Young's moduluses. So we have to take care of all the things. So this is continuous system. In this continuous systems, we will be dealing. Okay, so in continuous systems, for example, so what will be the learning objectives in the continuous systems? Continuous systems learning objectives will be. So let me crop this. So the learning objectives from the continuous systems will be, after studying this chapter thoroughly, so the learning objectives after going through this chapter, or after at the end of this live session, we will be able to derive the equation of motion of continuous system from the free body diagram concept of an infinitesimal small element of the system and Newton's second law of motion. So what will be we doing? For example, we are having a continuous beam, we are having a continuous string, we are having a continuous shaft. We will do one thing: we will discretize that the system into smaller number of infinitesimal number of these elements, and we will take that single one element, draw the free body diagram for that element, and use the same second Newton's second law of motion to derive the equation of motion for our. So what we are doing is we are taking only infinitesimal small element in our continuous system, and use the Newton's second law of motion along with the free body diagram concept. We will be deriving the equation of motion. Okay, so once we derive the governing differential equation of the motion, we will find the natural frequencies. Okay, natural frequencies will be our first target. Then there will be the mode shifts, that is determining the modal characteristics of our continuous systems using harmonic solutions. So we will be dealing with the harmonic solutions only. Okay, where we will be targeting the solution as x w of x comma t. That's the mathematical solution for the displacement with respect to space and time will be of the form sine omega t plus 5. Okay, we will determine then the free vibration solution of using linear superposition of modes and the initial conditions. Okay, this will be the initial condition problem. Obviously it's a dynamic problem. Okay, and we will be finding the free vibration solutions. Okay, with free vibration solutions we will be dealing with, one will be with the string. Okay, this will be for string, bar, shaft, beam, and membrane problems. Okay, but we will not be able to cover all these things in today's live session. We will limit our discussion to string, bar, or maybe beam if time allows us to discuss these things as well. Okay, so let's see how the session proceeds. Okay, then we will be able to express the vibration of an infinite string in form of traveling waves. Okay, then we will determine the forced vibration solution of continuous system using mode superposition method, and we will find the effects of the axial force, rotatory inertia, and shear deformations. Otherwise, these are later objectives. Okay, I think we will not be able to cover these things. Okay, so let me first thing first. I will show you what. So first will be, for example, we are having. Sorry. Okay. So for example, if we consider a string attached like this. Okay. Okay. If we consider a string, sorry. To make it. Sorry for the disturbance. Okay, for example, we are having a string like this. Okay, this is a taut string like this. It's having some span. L is the span. Okay, it's being acted by some dynamic loading like. let's assume dynamic equation x comma t. We will derive the system governing differential equation for this type of system as well. Then we will have a bar problem. For example, we are having a bar like this, okay, and its density varies like rho x comma t. We are having a x comma t, and it is being acted upon some force, okay, q of x comma t. So this is also one type of continuous system. Another continuous system will be, for example, we are having a this is this one, and transverse bending of beam. So this is load acting upon our beam. So if a load q of x comma t acts upon a continuous beam whose parameters are like this same, its density varies rho of x comma t comma a of x comma t, and we have rho a and another parameter, so q of x comma t, and it's considered as a simply supported case. Okay, this thing. So this is also a type of continuous systems. Okay, these are the things, q of x comma t, this one. So string, we will be dealing bar, string problem, in fact, bar problem, and this is beam problem. Continuous system. There are other things like stretched membrane problem. One is also the rotating shaft. We have other things, or the vibrations of columns as well, but we will not be discussing those things because I think we don't have that much amount of time to discuss those things. Okay, so these are the just basic things we will be discussing today. Okay. These are the continuous systems. Okay. Continuous system that we will be dealing for today's case. Okay. So starting with the first one is the transverse vibration of a string or a cable. Okay. So first one is transverse vibration of a string or a cable. Okay, this thing. So for example, if we consider a string like this, tightly stretched elastic cable of length L. Okay, this is the total length of the cable. This is the total length of the cable L, subject to a transverse force F of x comma t. Okay, this is a transverse force F of x comma t acting per unit length of this cable. Okay, and we assume the transverse displacement of this cable as along the z direction as w of x comma t. Okay, it will be the function of this. Equilibrium of the forces in z direction can be obtained by we have the equilibrium. Okay, so for example, if we select I will just magnify the same thing. So this is the small part of the cable AB. Okay, if we will just magnify it and take it here, this is the same thing. Okay, so this one f of x comma t. Okay, small infinitesimal part of the cable of length dx. Okay, dx comes here, dx is here. Okay, then at, for example, if we assume at point A, okay, point A it is having displacement w, then at point B it will be having displacement w plus dw. Okay, this is clear to you guys, and ds will be the arc length of this cable between the points A and B. F of x comma t is already acting there. This is the coordinate system. This is along span x, and this is along transverse displacement w. Okay, w of x comma t. So one more thing, the slope at this point will be here, it will be theta. Okay, for example, if I magnify it here, so if I sorry, if I draw a tangent at this point like here, okay, and along the horizontal, if I see how much it was making angle, I will consider it to be theta. Okay, then if I draw a tangent at this point as well, okay, and if I will see the angle made by it with the horizontal, it will be theta plus d theta. Okay, clear to you guys? So this is the simple basic things: theta plus theta and d theta, w plus dw along the length dx, where ds is the arc length. Okay, so if we write the equilibrium of the forces, so we will be having these equations. Okay, okay, 1 second. So along equilibrium along vertical direction, equilibrium of free body diagram. So FBD is this. Okay, this is FBD, equilibrium of free body diagram along the direction. Okay, so along that direction, so we are having one force P acting here, P plus dP. So its vertical component will be P plus dP, and one more thing, we are taking this direction as positive. Okay, and this direction as negative. Okay, P plus dP, its vertical component will be P plus dP. This will be horizontal, will be cos theta plus d theta. It will be sine theta plus d theta. Okay, sine theta plus d theta. Okay, this is clear to you guys. And then we are having force F of x comma t. So on length dx, force of F of x comma t times dx will act, and it will be acting in upward direction as well. But at point A, force P is acting with the with an anti-clockwise direction, so it will be having negative component. Okay, so and its vertical component will be P sine theta. It will be minus P sine theta. And one of the important things that I need to mention for you guys here is that, so it is acting like this. Okay, so as per D'Alembert's principle, in order to convert this system into dynamic equilibrium system, so that we can write the equation of the motion at each infinitesimal time point, so we have to apply a fictitious load okay, fictitious load to it, which will be directly proportional to m, mass of the system, times the acceleration of the system, mx double dot. So I will be writing mx double dot for this system, but mx double dot here both are mass is not known, so we will be writing it in terms of I mean to say that this uh, uh, we will be writing mass in terms of linear mass density times the length of that string. So linear mass density is rho. Here it is having a linear mass density rho. You don't consider it with the volumetric density. Okay, this is linear mass density. Okay. So first term m will be then equal to minus in place of m we will write rho dx. Okay, we will write rho dx, and we know that x double dot, we can easily rewrite the acceleration, but here it's not x, sorry, I have written the coordinate, so it's not x, it's w. Okay, m w dot. Okay, so similar will be w dot will be equal to acceleration, w dot will be equal to dou to w by dou t square. Okay, this is simple, very simple. Okay, it would be rho dx dou to w by dou t square, and whole will be equal to 0. This is a simple thing. And I already mentioned P is the tension, this spring, rho is the mass per unit length, theta is the angle deflected on the x-axis. Okay, and for element dx, okay, one more thing. Element of length dx, we know that dp at the end, that is this total differential dp at the end b will be equal to partial differential dou p by dou x times dx. This is the basic mathematics. Okay, the basic differential calculus. And if theta, we are assuming the deflections to be very small, so sine theta will be then approximately equal to tan theta. Okay, within the small angular deflection, and tan theta, we people know that it is the slope at a point. Okay, that is dou w by dou x. Basic mechanics things. Okay, you have to remember these things. So how we can write sine theta plus d theta? Okay, sorry, we have to write one more page. So we can write sine of theta plus d theta is equal to can write approximately equal to tan theta plus d theta, which will be equal to tan theta is first. So if we will expand this thing, we will get dw by dx plus dou to w by dou x square dx. Okay, similarly not considering the higher order terms. Okay, these things we got. So if we put these things here, sine theta plus d theta, we will substitute. This is equation first. So substitute. This is equation second. This is equation third. So I will write here, substitute 2 and 3 in first. We get, okay, so first we have to write p plus dp, we have to write it as p plus. So first this thing will be simplified here. P plus dp, something we will get cancelled. Okay, so some terms will be cancelled there, then we will be left with these things. First p plus dp will be here. P is there only, but dp is dou p by dou x and dx. Dou p by dou x dx. This is one thing. And in place of sine theta plus d theta, you have to write dw by dx, okay, plus dou 2 w by dou x square dx. This is one thing. Then plus f dx, it's always there. Then we have minus p is there, p sine theta. Okay, p sine theta will be dw by dx. And we will transpose this term to the right hand side. Okay, so this will be equal to rho dx, rho of x dx dou 2 w by dou t square. Okay, this is clear to you people everywhere. Okay, so throughout we can cancel the dx, and this p dw by dx and this p dw by dx will be cancelled. Once doing all the simplifications, we will have the equations like dou by dou x of p dou w of x, dou w of x comma t by dou t, no, with respect to space dx, it will be equal to, it's plus f of x comma t, because dx is cancelled throughout the equation, is equal to rho of x dou 2 w by dou 2 w of x comma t by dou t square. Okay, so forced vibration equation of non-uniform string. Okay, so if the string is of uniform and the tension is constant throughout, then we can write the equation in a simpler form. Okay, so let me first categorize it as, we got this. So this is governing differential equation for forced vibration of non-uniform string. Why it is non-uniform? Because here the linear mass density is also varying, and the, this tension is also varying. So we will write one more category into this: if the string is uniform and tension is constant. String is uniform and tension is constant. Then our equation will boil down to P, because here P tension is constant, so it will come out of the differential. It will be dou 2 w by dou 2 w, which is actually a function of space and time, divided by dou t square. Dou 2 w by dou t square. Okay. Dou t square. One more thing, and forcing function will be actually there, f of x comma t, and it will be rho of x. Rho will not be a function of x because it's uniform, it's rho dow to w of x comma t divided by, it's x square, sorry I'm writing it again wrong, x square divided by dow t square. So this is for uniform string, okay, for uniform. So what will be the case if f of x comma t is 0? For f of x comma t is equal to 0, we obtain free vibration. So the string is not under any influence of any external force. So we term that vibration is free vibration, okay, free vibration, okay. So in that case, free vibration equation will boil down to P dow to W by dow x square, and W is a function of x comma t, and it will be equal to rho dow to W by of x comma t divided by dow t square, okay. Simple. This is a free vibration equation for a string, dot string. It's a very famous equation, okay, keep that in mind. 1 second. Okay, we got these things, and we write this equation in a more standard form. Okay, this equation is written in a more standard form. The same equation we write it as c square dow 2w by dow x square is equal to dow 2w by dow t square. It's a very famous notation of this equation. Okay, another form. Free vibration equation, okay. Another form of free vibration equation where we will define the c parameter as, c parameter is known as c is equal to square root of, so see, you can see that p by rho is actually p by rho, okay. Rho, if we transpose to the left hand side, it is p by rho, okay. It's like this, p by rho, okay. This is known as wave equation, the famous wave equation. In physics you would have studied this thing. Okay, we reduced the governing differential equation for a string, dot string, okay. So what will be the initial condition for this type of motion? Okay, okay, so initial condition will be, so if we discuss about the initial conditions, so for example, initially this starts vibrating at x w such that the displacement w of x at t is equal to 0, okay, time 0 is equal to w naught of x, and also dow w by dow t, that's the velocity, at x t is equal to 0. There's the velocity imparted in the string is represented by w dot naught of x. Okay, these are the initial. This is the notation, in fact. So, for example, if the string is fixed at an end, say x is equal to 0, then w displacement w must be 0. So the boundary condition will be for string fixed from one end. Fixed from one end. And say x is equal to 0, we will have the boundary condition w of x comma x is equal to 0 comma t. Here the time initial condition is not there. Here it's some different case. X is equal to 0 at any time t, it is equal to 0. It's another type of initial condition. For all time t greater than or equal to 0, throughout the motion of the body it will be 0. So if the string of the cable is connected to a pin and can move in a perpendicular direction, so we can have different types of boundary. So in this case we have a different types of boundary condition. You people will see that yourself. Okay, so now we want to see the free vibration equation and the solution for this problem. So we can do one thing, free vibration solution. Okay, we will see free vibrations of string. Okay, free vibration of string. This is the thing. So let's assume that the displacement that the string goes through, that is w along space x comma t time t, we can discretize that. We can bifurcate that thing into two independent parameters, w of x, which only depends on space and is constant through time, and t parameter t, that is constant through space and but varies along time, w of x comma t, t of t. Okay, so if we now we have this equation. I will create this as equation. What was the last equation number? It was second. We were third. We were having this equation as 4. Okay, this equation as 5. Okay, this equation as 6. We will term this equation as 7. Okay, so in equation 7 we need dou 2w by dou x square and dou 2w by dou t square. So we will do differentiating with respect to x and t twice. Okay, so what we, if it is, this equation will be 8th number. Okay, so dou 2w by dou x square will be equal to, so t will be constant, t it will be dou, it will not be dou, it will be d, because it's not the partial derivative right now anymore. Okay, so w is totally dependent upon x, d to w by dt square. This is one thing, and dou to w by dou t square along time, second order derivative along time will be it will be w times d to t by dt square. Okay, square. Okay, so I am terming this whole system as 9th. Okay, so using 9th in equation 7, so using 9 and 7. Okay, we will be having this thing. Okay, we will be having, first is c square, it is c square dou 2w by dou x square, so it will be t Now d2 w by dx square, which is equal to w d2 w by dt square. Okay, this is the thing. So d2 t by d2 t by dt square. Okay, if we rearrange the things, we will be getting this thing c square by w d2 w by dt dx square. We will get 1 by t d2 t by dt square. Okay, these are the total derivatives right now. Okay, so let's see whole equation 79, let's say 10 boils to some constant a. Okay, it boils to some constant a. So when we will be writing this equation as c square w by dw by d2 w by dt square dx square is equal to 1 by t d2 t by dt square, which is equal to a. Whole is equal to a. Okay, 1 second, give me a moment. Okay, this is whole equal to a. So this can be I mean to say that written into two equations. We will have two equations from this one. We will have two equations. One equation will be c square by w d2 w by dx square will be equal to a, or we will be having 1 by t d2 t by dt square will be also equal to a. Okay, these are having two things. So first equation we will write d2 w by dx square minus a by c square, because these are constants. A by c square is constant, w is variable, w is equal to 0. So we can term this as 11, this is 12. Okay, and 12. So this is from 11, this one thing. Okay, so this is a simple second order linear differential equation. We can write the solution for this thingy. Okay, so for this thing we can convert this equation like this: d2 w by dx square plus omega square by c square. Okay, time w is equal to 0. Okay, so we have this thing, and this equation we can write as, from this one we can write as d2 t by dt square minus a times t is equal to 0. This is also a second order linear differential equation where we can convert it into d2 t by dt square minus omega square t is equal to 0. Okay, where we are writing omega a is equal to omega square. Okay, where a is equal to omega square, keep that in mind. So we can write the solutions for these two. These are well-known equations. We can write the solution for these two differential equations like this. For the solution we can write, so displacement part along the space w of x will be then equal to a cos omega x by c plus b sine omega x by c. This is one thing, and we can write t as a function of time t as c cos omega t plus b cos omega t, b sin omega t. These are the two parameters, important parameters. So this will term as 13. Okay. So for example, this is 13th equation. Okay. These are the two things. So let us assume the boundary conditions like this. If the string is fixed at both ends, then the boundary conditions are, I will assume assuming string fixed at both ends. So for that we will be having the boundary condition wx is equal to 0, it will be equal to 0, and w at x equals l, it will be also equal to 0. Okay, and for that if we substitute these substitute in 13, substitute this equation in 13, we will get the value that a should be equal to 0 at any cost, a should be equal to 0, and in order to satisfy the same thing, b sin omega l by c, please check it carefully yourself. Okay, this is very simple. B sin omega l by c should be equal to 0, but b cannot be 0. Okay, so that because the w part will vanish totally, so then b will not be equal to 0, then sin omega l by c, c should be 0 at any cost. Okay, so yeah, then equation this sin omega l by c is called the frequency or characteristics equation, and it is satisfied by several values of omega. Okay, the values of omega are called the eigenvalues of the natural frequencies of the characteristic values of the problem. The nth natural frequency can be given by as, we know that sin omega l by c, this is known as frequency equation. Okay, frequency equation and eigenvalues. Values are frequencies and eigenmodes are vectors, and eigenvectors are mode shapes. Okay, mode shapes. Okay, so for sin omega l by c is equal to 0, then omega n, that's nth natural frequency, omega n l by c should be equal to n pi, because for each integral value of pi, sin is equal to 0. Okay, n pi. Pi can be run from, n can run from 1 to up to n. Okay, so this is the nth natural frequency of our problem. Or we can write omega n precisely clearly as nc pi by l. Okay, we derive the natural frequency of our system as, and it's for free vibration problem, nc pi by l. So this is natural frequency. Nc of string. So if we substitute these values back into w of n x comma t, which is composite of w of x comma t and t of w of x and t of t, like here. So if we substitute the three back these things, we can get for nth mode transverse displacement w of n comma x comma t, which is function of both. We can write that as nth mode displacement along x and t parameter in the nth mode of t, it will be equal to, okay, this will be whole equal to w of n x comma t will be equal to then sin n pi x by l. Okay, because a is equal to 0, I already proved that. Okay, and for nth mode along t, we can write Cn cos omega is n pi L by C, okay, n pi n C pi T by L, okay, Cn dn, sorry, this is sine n pi C T by L, okay. So if there is also time initial condition, we can find the value of C and dn. That depends upon the problem to problem, okay. No, you can do that thing as well. This is the Gaussian differential equation for the free vibration problem string. Okay. So this is the thing we deduced. So there can be the different modes for the same thing string. So depending upon the value of n, we'll have different types of modes of our string. So depending upon value of n, we have different modes. As like this, we have different modes. First mode will be like so it will be first mode may be like this, okay. This is for n is equal to 1, okay. So if n is equal to 2, what will be the case? Same string of same length, so we will be having one cut. We will be having one like this, that will be having like this, okay. Same thing will be like this motion, because it will repeat now up and down, okay. So this may be like this. This is for the mode shape if less frequency and second motion n is equal to. So similarly it will be, because, and one more thing important, I have to keep that in mind. I'm not making it as fixed because we assume w of x is equal to 0 is equal to 0, w of x is equal to l is equal to 0. These are the important boundary conditions you have to keep that in mind. Know that form is the basis for deriving the free vibration problem. So if n is equal to 3, we will be having same string tossed at two ends, but we will be having 3 crossings, okay. Like this, okay. Same will be like this here, from here, from here, okay. So like this, n is equal to 3, and fixed details from both sides, like this, and we have this is O, this is O, this is O, okay, and we have this is, and the modes will cut at, this is at L, this is L by 2, okay, it's up to L, this is L by 3, this is to L by 3, and this is again L, okay. So this is the x-axis, this is x-axis, this will be vibrating along x-axis, and the same is from the case along, this is a case along displacement in nth mode Wn, where n will vary, displacement in nth mode, displacement in nth mode. Okay, these are the things you have to keep in mind. N is equal to 1, n is equal to 2, n is equal to 3. These are the mode shapes of a cable. Okay, n equals 1, n equal to 2, n equal to 3. Okay, these are the mode shapes. So I think we already have taken a lot of time. I think I need to stop mode shapes. Okay, so we only solved it for found the coordinate differential equation for dot string only and solved the free vibration problem. So after this, we had to discuss about longitudinal vibration of a bar and the later vibration of beams. I think I will keep this thing as a to you as a part of your homework, and in the presentation maybe I will add the derivation as well. So you can also try these things on your side also. So I think this is all for today. Thank you so much for joining. Okay, thank you. The people can leave.